So because I'm gone today, we're going to talk about Chapter 16, Introduction, through a video. In Chapter 16, we're going to discuss the kinetics of chemical reactions. We'll think about how fast reactions occur and how we can model how reactions happen over time. The reason that we care about kinetics in the first place is that up until this point, we've only really talked about how likely a reaction is to happen, but not when a reaction will happen or how long a reaction will take in the first place. The reason that we care as chemists about how long it'll take a chemical reaction to happen is that even though some chemical reactions can be thermodynamically favorable, like this reaction of H2 and O2 to form water, which overall results in a decrease in enthalpy and should be favorable thermodynamically in the eyes of the universe, is great because we could solve the world's water crisis, except this reaction, if you extrapolate data, could take 10 to the 25 years to occur. Place these same reactants in a flame, though, and the reaction between hydrogen and oxygen to form water might only take a microsecond, 10 to the minus 6 seconds. So it's important that we as chemists understand how long it's going to take a reaction to occur, because we'd like to know not only whether a reaction happens, but also whether a reaction will happen in our lifetimes or in some reasonable amount of time. There are three key factors that influence the rate or speed with which a reaction occurs, and they're all predicated on the postulate that in order to react, particles must collide. This idea of collision theory is in turn dependent on three things. Firstly, concentration. And this might seem intuitive. The more stuff there is, the more reactants we have, the higher the likelihood of reactants bumping into each other or colliding and having the opportunity to react in the first place. So as concentration goes up, generally speaking, reaction rates go up. The second driving force behind reaction rates in collision theory is surface area. And this really mainly pertains to reactions that happen with or on solid materials. We can think about solid materials as offering greater surface area if they're, say, ground up into dust versus bulk materials, where it's just one big chunk of solid. Greater surface areas mean that there is more space for reactions to occur, a greater number of sites where reactions can happen. Thirdly, temperature is a major driving force for the speed of a chemical reaction. Remember in General Chemistry 1, when we discussed the kinetic molecular theory of gases, we said that increased temperature translates to increased average kinetic energy for particles. And generally speaking, with increased temperature, molecules have increased average kinetic energy and can therefore move faster. Faster moving particles both increases the frequency and the energy with which particles will collide. In this course, we're going to focus primarily on the first and the third driving factor of reaction rates, concentration and temperature. We'll first talk about concentrations. To examine the influence of concentration on reaction rates or speeds, we have to be able to write down an expression that shows how concentrations influence the rate of a chemical reaction. We'll call these relationships rate equations. Eventually, we're going to set up differential equations, which will require us to use some calculus to solve. I know that not all of you are in calculus, so you will not have to reproduce any calculus, although we will do some in the course so that you can see where these equations come from. In order to set up these equations in the first place, we're going to take some generic reaction, where some reactant, any old reactant A, undergoes a chemical transformation to become product B. Think about what's happening in this reaction. We're reacting away A, so it's disappearing, and we're producing B. B is appearing. Suppose that we set out to perform an experiment where we monitored either the disappearance of A or the appearance of B. we could time how long it takes for either A to disappear or B to appear and represent that graphically. So, let's talk about that. So all I've done here is set up some axes to plot concentration on the y-axis of either reactant A or product B versus time on the x-axis. We're going to think about how concentration changes as a function of time. If we wanted to monitor, say, A disappearing, we could expect that A starts somewhere up here on our plot and decreases in concentration over time. Maybe it looks like a straight line relationship. Separately, if we wanted to think about product B appearing, we would expect B's concentration to start at 0, there's no B originally, and it to increase concomitantly over time by the same amount that A decreases. So what have we got here? We've got concentration of B plotted in green, concentration of A plotted in blue. A is disappearing and B is appearing. What's the rate at which A is disappearing, or the rate at which B is appearing? Well, you probably remember from math class that we can express the rate as a slope of a straight line. If we had plotted, say, distance along a y-axis versus time on an x-axis, we could express speed as distance over time, or the slope of a straight line graph. And in the same way, we can express rate of change for chemical reactants or products as a function of concentration change versus time. To get a slope of a straight line, we just take 2 points, point 1 and point 2, and we calculate a delta y over a delta x. That delta y is y2 minus y1 over x2 minus x1. That's the slope of our straight line. Well, what happens if our picture for our reaction doesn't look like a straight line? Perhaps instead, the concentration of A changes like this plot in blue, and the concentration of B changes like this plot in green. These are no longer straight line relationships, but the way that A changes is mirrored in the way that B appears. In order to evaluate how concentrations are changing over time, this is where we need to use some calculus. We can still calculate the slope, except we just calculate the slope at a single point. So what's the slope right here? Your textbook will tell you that it's still delta y over delta x, but we're going to write that same information slightly differently. We're going to say that it's dy instead of delta y over dx instead of delta x. And the difference between these d's and the delta we saw before is that these mean an instantaneous point in time. What we're really doing is finding the derivative of this blue curve at this point that I've drawn in on the graph. Generally speaking, we express the rate of a chemical reaction in terms of the change in concentration of a reactant, say dA, over time, dt. Concentration of A is what's on our y-axis here and plotted in blue. Change in time is what's on our x-axis. And what's more is we'll notice that our blue line is sloping downward right at this point I've drawn in. In order to account for that downward slope, we're going to put a negative sign out in front of this. The rate is equal to the negative change in concentration of A, that's what this dA means up top, over the change in time. That's what this dt means down at bottom. Negative dA dt is our rate of change for this chemical reaction. Suppose instead we had monitored the rate of increase of product B, and we're looking at the change right here at this point on our green plot. At this point, our change in concentration is the slope right at that point. That's the change in concentration now of B as time changes. In this case, This plot is sloping upward. The change in concentration is positive. We're increasing the amount of B. So we don't put any negative sign here. We can equivalently express the rate of a chemical reaction as the negative change in concentration of A over time, or the positive change in concentration of B over time. In order to give you some sense for what I mean by expressing rates through these differentials, I'll show you a real-world example. Here, consider the reaction of ethylene C2H4 with ozone to produce C2H4O and oxygen. Suppose that we monitored reactant ethylene C2H4 and watched as it decreases over time. It slopes downward, but not in a straight line. Or we alternatively watched the production of oxygen, O2. O2 begins with zero concentration because there's no product originally, but over time slopes upward as it increases in concentration as our reaction progresses. The downward slope of our reactant, C2H4, mirrors the upward slope of our product, O2. We can write the rate for this chemical reaction as either the negative change in concentration of our reactant over time or the positive change in concentration of a product over time. We could equivalently have said that the reaction rate is equal to the negative change in the other reactant, ozone, O3, over a change in time, DO3 dt. Or, again, equivalently, the change in concentration of our other product over time, C2H4O. This is positive because products are being produced and they're increasing in concentration. All we have to do to write down a rate expression using these differentials is to use a negative for any reactant, because reactants will disappear to produce products, a positive sign in front of any products then. Express the change in concentration of a reactant or a product using D, concentration, and a change in time using dt. One last example of how we write down these rate expressions. Here I've given you two different reactions. One generic reaction where A moles of A plus B moles of B becomes C moles of C and D moles of D. And one normal equation, that reaction of H2 and O2 that we started with. Two H2s plus an O2 become two H2Os. When stoichiometric coefficients other than 1 are expressly present in a chemical reaction, then we're going to have to account for those stoichiometric coefficients by normalizing the amount of change of any reactant or product in our rate expression. Let me show you how that's done. Consider first reaction number 1, where A moles of A react with B moles of B. We could express the rate for this reaction by watching either of our reactants disappear or either of our products appear. If we watch a reactant disappear, say reactant A, we expect a negative change in concentration of A over time. But we'll notice that we have differing amounts of A and B. We need to account for that difference in stoichiometric amounts, and we do that by dividing by our stoichiometric coefficient. I could have also equivalently expressed the rate of this chemical reaction in terms of the disappearance of B. Instead, I'd put a negative sign out in front and express the change in concentration of B over a change in time, but I'd also have to normalize this change because of the stoichiometric coefficient little b out in front in this balanced chemical equation. So I divide by little b, the stoichiometric coefficient. I could have alternatively expressed my rate in terms of the production of, say, product C as a function of time. This is a positive value because products are produced, but I still have to weight it or normalize it by its stoichiometric coefficient, 1 over C. Similarly, I could have looked at the rate of increase in concentration of D over time, again a positive value because D is a product, and I'd have to normalize that or weight it by dividing by its stoichiometric coefficient, little d. In our final example, we'll consider the formation of water. In this reaction, 2 moles of hydrogen react with 1 mole of oxygen to form 2 moles of water vapor. To express the rate of this second reaction, we can consider either the disappearance of hydrogen or of oxygen or the appearance of water. As we consider the disappearance of hydrogen, we know that its concentration will change by decreasing over time. And we have to account for the stoichiometric coefficient here by dividing by it, too, or multiplying 1/2 by our expression. Equivalently, if we had watched oxygen disappear instead, we could have expressed the rate of this reaction as negative change in concentration of oxygen over change in time, divided by 1. 1 over 1 is superfluous and unnecessary. Finally, we could have watched, instead, water being produced, in which case we would expect a positive change in concentration of H2O over time, but weighted by its stoichiometric coefficient, divided by 2 or multiplied by 1/2. Each one of these rate expressions that we've written here for both reaction 1 up above and reaction 2 down below are equivalent to each other and are the necessary first steps in being able to write a rate equation and ultimately being able to solve for how reactions components change over time. And this is what we'll do in class when I return.